So let's take a look at the SRK equation of state, and let's start here in the props table. And what I wanted to show you is that if you just type in dimethyl ether, as the problem statement says, you're not going to get anything. But if you just search for ether, you'll find a number of them, and you can see that the abbreviated form for dimethyl ether is DME, and you can keep just searching for that, and you'll see all the different kinds of ether that we can have. And the reason we use the abbreviated form, if you can imagine, if you had to do these calculations for DME over and over again in a process that you were working on, you'd get tired of typing all those letters. So in the long run, I think it comes out shorter using the abbreviated forms. So now we can go back to here, and we would want to type in DME again, just to be sure. And we can see that it's loaded up the properties for DME, and this is our standard SRK equation of state on the EOS props tab. And you can see that for DME, the only thing that we know is the lead constant for the heat capacity. These other values are 0. Now I'm going to do some little bit of tricks here because I want to be able to show you these parts of the calculations while we're discussing the problem statement on the same screen. So what I'm going to do is I'm just going to assign this t value to be equal to this one that I'm going to just temporarily use. The p value similarly is just equal to that, and I've just made a copy of this value here. Actually, why don't I just set that equals? And so that we'll be able to work over in this part of the screen without having to flip back and forth, and that'll be a lot less distracting. So let's do that. And I'll just move this like that, and then I'll go back to here, and I guess we could make this work. I don't know. I think it'll be easier if we just make that smaller and go like that. Yeah. I think you can see all the key points here. If we've got our conditions A, B, and C here, so that'll work. And so now let's move this over into the zone where we can actually do our work, and then we can read the question and then answer it. I think we can make this slightly bigger now. Alright, so we've got our temperature, our pressure, our heat capacities. I've computed this fugacity ratio here. It's the ratio of these two fugacities where these things are just equal to the values that were calculated on the left-hand side. Okay. Right, we've got everything we need. So, to get part A, then you can see that I've typed in the temperature and the pressure of 45 and 1.5. So for part A, what's going on? Why isn't that working? So what we want to write out, see this thing here? Let's write that out. So this is H at 45 and 1.5 minus H ideal gas. Well, if you think about it, that's this quantity. Let's see, is it a vapor or is it a liquid? Well, we have to decide based on the fugacity. And the fugacity of the liquid is lower than the fugacity of the vapor, so that means that's the stable root. So we should be using this number, -179. Nope, 17279.8. Okay, Now then, we need the H ideal gas minus the H ideal gas part. Well, that's just 6, so let's write that out. H ideal gas at 45 minus H ideal gas at 25 is equal to 65.73 times 45 minus 25 is equal to 1314. You got your calculator? 0.6. That's what I'm getting. All right, so and then this part, since the reference state is the ideal gas at 25, that part's just 0. So we can say then that H is equal to negative 17279.8 plus 1314.6, and the number I get there is negative 15965.2. All right, so let's look at part B then. That should be easy because here all we're doing, this is the same, Tref is the same, and now we're just looking for the saturated liquid. I guess it doesn't matter for H what Pref is because for the ideal gas there is no enthalpy change due to pressure. And so you kind of get that sense when we just write that H ideal gas is only a function of temperature. All right, so now we have to, so then we've got H minus, now we got to add this part here, right? So we got to get H ideal gas minus H at 25 and looking for P sat here. Okay, so we have to get P sat. And so, well, in case you hadn't noticed this before, I'll just show it to you. So over here it shows you in big red letters that the stable root has the lower fugacity. So we're just following that. Well, obviously, if you want the vapor and the liquid to be in equilibrium, then neither one should have a lower fugacity, which means they should be equal. And so to find the saturation condition, what we have to do is set this to 25, and we want them to be, so we want this fugacity ratio to be 1. So let's try let's just try 1, something smaller. You can see that we're heading in the right direction. So from here, I'm just going to call the solver something's not right. You can see that we're trying to solve this fugacity ratio, so that's cell N6, to a value of 1 by changing the pressure. Yeah, that's right. I don't know why it was harassing us before. And it seems to have found an answer. So, great. Now, so we found H ideal gas. So this is for the liquid, saturated liquid is what we want. And so that would be, this is the liquid root. So it looks like we want the number negative 1/800. So this is equal to negative 1/800 18,200.0, right? Wrong. Because this is H ideal minus H, and this is H minus H ideal. So we have to put a plus sign there. Okay. Now, oh, I think we're not done yet here. So to get H for this saturated liquid, well, the other two parts of the path are the same, so then that's just going to be equal to negative 15965.2 plus 18200 and 0.0, and that's equal to 2234.8. God, terrible handwriting. Nope, 8. Okay. What just happened? Now I don't know what's happening. And C, we need to go from 386 to the saturated liquid. So H minus H ideal gas. Let's write down what it is. H at 386 and 1.5 minus H ideal gas is equal to, let's go calculate that. So we want to make this 386 and 1.5. What happened? Yeah, that's right. And okay, everything else is okay. And you can see that we switched into the 1 root region because this temperature is supercritical. So we have to use that stable root of negative 401.0. Okay. Now then, for H ideal gas at 386 minus H ideal gas at 25, that's equal to 65.73 times 386 minus 25, and that is equal to 23728.5. All right. Now, then the last part is going to be H ideal gas minus H of the saturated liquid at 25, which we already know. All right, so H is equal to negative 401.0 plus 23728.5 plus 18200.0, and that number is equal to 41528.5. All right, so that is pretty much the solution to this problem. So if you'd like to stop, go ahead and stop. That's fine. But I thought I might show you a little bit of a bonus calculation here. So because state C and state B have the same reference state, then what we can write is that delta H of C minus B, let's say, is equal to HC minus href minus HB minus href. And because this is a negative href and this is a negative of a negative href, they cancel out, right? So this should just be equal to 415.28.5 minus 2234.8. And that's equal to 39294.0. Well, there's something off there. 0.5. Oh. 415.2234. Let's just forget the 0. So here's another way of solving that problem that I think you'll see is a little bit quicker. So I'm going to go into full screen here. What you realize is that there are various possible reference states. And if we use this sheet in a certain way, we can choose whichever reference state we want to make our calculations a little bit simpler. One of the main ways to go wrong in these calculations is to mess up your positive and negative signs. When you choose this particular reference state, and we've already seen that the reference state doesn't matter, it cancels out at the calculation. When you choose this one, you almost always get positive numbers so that you don't end up subtracting a negative number which has to turn into a positive number, and that gives you a chance to make a mistake. So let's try and do this final bonus calculation just using the reference state as given. And so what we see is that the H relative to the default reference state is 4685.9. So let's write that down. Something went wrong. 46. What did I say before? 859.16 minus the starting condition, which was 45 degrees Celsius, and 1.5. Right, that's what our delta H is. And so that number is 7565.15. And so we see that we get the exact same number regardless of our reference state.